And who am I going to play? All right, I'm going to be, let's see. I'm going to have another nickname here. I'll be this person. There we go. Let's start it off, ladies and gentlemen. Skip. All right. 4 seconds. Lennon's in first. Shayana's in second. Cami is in third. Good job, guys. Okay, so today what we're going to do, it was a vocabulary practice. Today what we're going to do is we're going to talk about the 4 fundamental forces. Okay, so to do that, we're going to do some poll questions. And if you're interested in the drawing at the end of the hour, we can do that. So let's take a look at the 4 fundamental forces. Let me double check to make sure if you can hear this or not. Tell me if you can hear this video.
The 4 fundamental forces of nature.
Anybody hear that okay when I turn that on? Okay, great. Thanks, Joey. Glad you made it.
Are like the language between particles, allowing them to interact in complex ways. From atoms to life to entire galaxies.
Thanks, Lennon.
But imagine that you had a machine that could turn each of those forces off. What would happen? Force 1, the electromagnetic force. It makes opposite charges attract and like charges repel. So what happens when we suddenly switch it off? All atoms in the universe fall apart. Negative electrons are attracted to the positive nucleus, like planets orbiting the sun. But without the attractive electromagnetic force, electrons simply fly away. And with no atoms to provide structure, planets like the Earth would collapse under its own gravity. Stars would also collapse, but then violently explode as supernova, leaving behind neutron stars or black holes. Force 2.
Okay, so let's take a look at the questions here. What happens when the electromagnetic force is suddenly switched off? All right, so we're going to have a poll at the giveaway at the end of the hour here. So the more people we can get in there, the better. So what happens? The electromagnetic force is suddenly switched off. Are the electrons are attracted to the nucleus? Electrons repel the nucleus? Electrons fly away, or electrons fuse with the nucleus? All right. All right, got one person that got it right. Let's see who's got it right. Thank you, Lennon. You got it. All right. Thanks, Ariana, Joseph, Shayana, for getting in there. Okay, so the correct answer on this one is letter C. Letter C is that the electrons fly away, because what's happening now is that the plus and minus charges no longer attract each other. So that's what the electromagnetic force does. It has, let me go here, change this to white. Okay. And go here. Okay. So the plus charges are attracted to the negative charges, but if there is no electromagnetic force, then these things would not connect to each other. They wouldn't be attracted or repelled. They'd go away, and all the nucleus, the parts of the atom would be, there wouldn't be any atoms, nothing to bind with, right? Okay, so let's look at the next fundamental force. The next fundamental force is called the strong force. And so the strong force is the force inside the nucleus. All right. And the strong force, we'll have a question on that. So watch carefully for the next, it's about a half a minute that they talk about
The strong nuclear force. The force that binds protons and neutrons together inside the nucleus of atoms, and also binds the quarks that make up protons and neutrons. So what would happen if we turned the strong force off? Well, the nucleus of all atoms would violently explode. Without the strong force holding the nucleus together, the electrostatic repulsion between positive protons would violently fling the nucleus apart like a tiny grenade. The neutrons and protons also break apart into a soup of individual quarks. The breakdown of the nucleus causes a universe-wide explosion of every moon, planet, and star. Force 3, the weak nuclear force.
Okay, so this is the strong force. And remember what they said in the strong force. The strong force controlled the positive protons in the nucleus. Okay, so what we had, we were to take a picture if we did this. So the protons, remember, are plus charges. Neutrons are zero charges. And to get another plus charge in next to it, it's impossible if it was gone. So the strong force has to have that proton be able to connect to another proton or a neutron, because if not, the electromagnetic force would overrule that and move those out. Okay, so what force, how does a strong force hold the nucleus together? Right, so how does that work? Does it by repelling protons, by binding protons and neutrons, by converting protons to quarks, by accelerating neutrons? Oh, we got Lennon and Joey. Thanks, Lennon and Joey. And we got Renaya. Thanks, Renaya. And we've got Bradley. Okay, so we've got 4 people together. All right, so the correct answer to that was, let me see if I can get the color here. Binding the protons and neutrons together. Binding the protons and neutrons together. Okay, so let's take a look at the video again. We got 2 more parts of this video to watch and a few more questions.
Nucleus needs roughly equal numbers of protons and neutrons to be stable. When this isn't the case, the weak force kicks in by changing neutrons to protons or vice versa. This process is key to nuclear fusion, the process which powers stars. So what would happen if the weak force stopped? Well, actually, not much, or at least not right away. The sun would immediately stop producing energy in its core, but it would take at least 10,000 years for that energy to reach the surface and then to reach Earth. The radioactive decay that helps to heat Earth's core would also stop, eventually causing a new ice age. This would also weaken our protective magnetic field, exposing us to solar radiation. Over time, this would slowly erode the atmosphere, turning Earth into a barren, lifeless planet, just like Mars. Finally,
okay, so let's take a look at this question here. So remember, the weak nuclear force causes radiation to happen, all right, and it keeps those, and it changes the neutron into a proton, and then particles are ejected. We get heat from that, and it causes fusion. So let's see what we got here. So what is the role, the weak nuclear force in nuclear fusion? It changes protons to electrons. It changes neutrons to protons. It activates strong nuclear force. It splits atoms. All right, we got one person got it right. Thanks, Joey. Anybody else? Hey, we got Zaria in here, and Tanisha, and Lennon, and Renaya, Kamaya, Kalia, Christian, Bradley. Good to see you guys. And we got 5 people this time voting. All right, so changes neutrons to protons, okay? So that's what the nuclear fusion happens in the sun. Also, it's how we keep the nuclear particles from becoming stable, so that is important in our lives here. It also heats up the earth, so changes neutrons to protons. Oh, I got that in black still here. All right, can I write on this or not? Nope. Okay, let's do this one. How about that? There we go. Neutrons to protons. All right, so the last one is about gravity, but let's take a look at this kind of recap. The strong nuclear force is the force that confines quarks into protons and neutrons and other hadron particles. It binds the neutrons and the protons to create atomic nuclei. So that was the strong force. The weak force, force that controls radioactivity and decay of unstable subatomic particles, begins nuclear fusion. Ooh, I got a cough again. Ooh. All right, true or false, weak radioactive force controls radioactive decay. True or false? Got 14 people here. 3 people so far. All right, so most people said true, and that's correct. True is what the weak force does. It changes a proton to a neutron. All right, so the last video we have is a section on gravity. So let's take a look at what it says about gravity. And if we could turn that off, what would happen to us?
Force 4. Gravity. The attractive force that pulls things with mass toward each other. What would happen if you switched it off? Well, back on Earth, any object not fixed to the ground would appear to start floating upwards. And with no gravity holding the atmosphere down, the air would literally get sucked out your lungs as it floats away into space. But don't worry, you'll be fine in your pressurized space lab, right? Well, no. 8 minutes after you switch off gravity, you start to notice the sun getting bigger. The inward force of gravity in stars balances out the outward pressure of its core. But turn gravity off, and the enormous pressure violently ejects the sun's superheated plasma into space. But don't worry, you have a few hours before the sun's plasma reaches you and cooks you alive. Thank you for watching. Please enjoy my other science.
Pretty terrible stuff when you think about it. All right, and those are kinds of things what happened with fundamental forces if they were not working. So let's ask this. What is the consequence of gravity being turned off? What's the consequence of gravity being turned off? Objects fall to the ground. Everything floats upward. Everything collapses. Earth collapses. Sun's core gets hotter. All right, so 3 people got that one right. Everything starts to float up, right? Because we don't have things holding us down. Right, so let's take a quick review of the 4 fundamental forces. The strong force binds the nucleus. The electromagnetic force, so that holds the protons and the neutrons. So these are the protons, right? And the protons can stick together using the strong force, right? But we need the electromagnetic force in order to keep the electrons orbiting around the nucleus with positive and negative charges. So we need that for sure, because electromagnetic forces cause electricity and binding of atoms to make different chemicals. The weak force is the force that controls radioactive decay and fusion. And then the gravitational force is the force between all objects that have mass and binds the solar system together. So which of the 4 forces binds the atoms together, makes electrons attracted to protons? So the right answer here is the electromagnetic force, because the electrons are negatively charged, the protons are positively charged, and in order for them to be attracted to each other, electromagnetic force has to be in place. The strong force connected the two positive charged protons together so they didn't fall away from the nucleus. The weak force was the radioactive part. All right, so last thing on our agenda today before I break you guys into breakout room is that you do, where are you? Okay, so we are going to, all right, so let me show you this. Oh, excuse me, guys. All right, so we have an exit quiz that has 4 questions in it. It is in the module. It's open until just 3 o'clock. Okay, so if you don't get it in, you don't get your bonus points. You don't get on so here is the link to that. It is in week 5. Week 6 is now open, right? So today I'd like you guys to finish up all of week 5's assignment. Week 5, 1 and 2 are due today as well. Here is the fundamental force quiz that you can do right now. 4 questions about the 4 fundamental forces. All right. There you go. Get working on that. I will open up a breakout room. All right. So if you have questions about your grades or you need some help with something, let me know. I will put that link in the chat.